All right, so what we're going to go through is one of actually the example, um, like real use cases that currently labs. Um, what we're trying to do here is we take a look at who has minted what NFT or minted from what NFT collection on Zora, basically on Zora's network. And then we're gonna do that person to collection signal as uh, the Hudson Authority's peer-to collection like graph, and then we're gonna use Hudson Authority's algorithm. And in order to do that, we need to do some sort of pre-processing to convert that peer-to collection data to peer-to-peer data. So it's really peer-to collection back to peer, so that we get some sort of similarity, like local trust between any two people based upon their shared interest in which collections and like how much of them. So that's what we're gonna do. So let's first take a look at the source table, what the data that we use. Let me share this one, change windows. All right, so this is the query. I'm gonna share later on in our office hour chat. And I'm for now, I'm just gonna show you result that we're getting, which is right here. So basically, I is the peer for EOAs, and J is the address of those collections. And then from I to J, the value is basically the US dollar equivalent of like um, funds that I has spent on minting J. And we if I the same I has minted multiple times from the same collection, then we add those together, like some of those together, and that sum basically becomes fee. So we have about 110K rows, which is pretty sizable. This will be pretty good for this exercise. So what I did, what I did was to first download this table and cache it as needed on like S3. So I'm gonna go through that code. Share back my book here. So since we'll be using both Dune and also S3 as the caching layer, we need Dune API access key, which you can actually get from Dune. Anyone can do this, and you can also sign up for AWS. And free tier should be able to handle this. So you don't have to spend that much money at all. So that's what we're doing here. And then basically put all these keys into the variable environment variable. Then we run some prerequisite steps of like installing everything as needed. And then here's the fun part. After setting up all the environment like Dune as well, like S3 or AWS, we now try to first load the IJV as CSV from S3 first. If it is there, actually no, like not CSV, Parquet. And if it is there, then we use it verbatim from S3. If it's not, then we download from Dune query. This query ID is the one that I showed you earlier, and then convert that into Parquet and save it into S3. I did this because I needed to run this like multiple times, and if I just like download it directly from Dune, then every single time I do that, then I'll be consuming some API credit from Dune. And for free tier, it'll dry up pretty quickly. So this is basically so that I can actually cache the contents, and so that if I change that Dune query, then I just delete that cached copy in S3 using the AWS CLI and do that again. So let me actually do it and show you. So I'm gonna in the notebook, we see the bucket ID and key name. Let's S3 LS S3 Zora test. Yeah, this is my own bucket. You can actually create your own bucket as well. So I'm going to delete S3 IJB. Okay, and once we did this, and if I run this again, then the console should say, hey, like I'm gonna download from Dune. Here we go, reading from Dune and caching on S3. It's gonna take some time, like 6 seconds, not too long. And then we downloaded all this table as we saw on the Dune query. Now, using this, we create peer-to collection and back-to-peer matrix. There are some explanations here. Basically, what we're trying to do is to create kind of two different copies of local trust, half local trust. The first step is peer-to collections, which is basically the same IJV we saw here, except we normalize this value so that from the same from the same person, we normalize this value that they actually sum up exactly 0. And that's actually what happens in code here. And same for C2P. C2P is J back to I, and it is also normalized so that for the same contract, the value for different i's is also to 0. So let's do this and then see the result. That was actually pretty fast, 0.3 seconds. And now, this is the heavy part. Now that we have this peer-to collection and collection back to peer matrix, if we actually multiply these matrices together, then what we end up getting is peer-to collection back to peer matrix. And this matrix has only peer IDs as its indices, none of the collections. It's a purely peer-to-peer matrix, and each entry on this matrix is how similar these two peers are. My entry in this matrix, and for example Andrew's matrix, entry in this matrix, will indicate how similar our interests are based upon the shared collections that we both minted from. And then so that's what's going to happen on this first line. And then we do this line, which means like set all the diagonal entries, which means from a person back to himself. Eigentrust requires that the local trust shouldn't have such diagonal entry, like self-referential entry. So we zero them out. And then we eliminate zeros just to make sure that it is a sparse matrix, because otherwise, like later operations will be pretty slow. And then finally, we transpose this P2P matrix. And the reason why we do this is eigentrust requires truster major matrix, which means each row ID or each row index should be the one that trusts the other people. And what we actually get here is trustee major, where each row and index is who is being trusted, not who trusts. So we actually reverse that relationship by flipping or transposing the matrix. And then finally, we are going to print this out, or the dimensions of it, so that we can do, okay. So that step was actually already finished. Detect low 64 with roughly 30 million non-zero entries, which is pretty sizable. By the way, this is why I'm actually doing this on local, locally hosted notebook under like PyCharm instead of using Hex.tech, because this is still a little too big. We're like Karma 3 Labs is working on some code changes to make this actually runnable using Hex.tech notebooks, but yeah, that's not quite ready. For now, we're doing this locally, and I'm gonna share this IPy notebook file as well later. And this is basically the number of peers, a number of distinct peers in this local trust matrix, we have roughly 22,000 people. And this one, yeah, the vast majority of this is this time is actually being spent on this line, because this is actually a pretty big file. And now that we have this, we 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 need to like use this in like eigentrust run, which I'm gonna do in the using the original full eigentrust command line function. But before doing that, we also need to first read pre-trust. So what we worked on so far is local trust, and we need to work on the actual pre-trust. Like Darmi here has worked on a few different flavors of pre-trust or seed trust, and these are all those variants. They are like I have locally downloaded them into CSV. Excuse me. Oh, 1 second. I had a cold. That's why. So we will also share these CSV files on the chat so that you can actually do this locally if you want it. And now what we're doing here is to load all these CSV yeah.
Sorry, 1 second. Just maybe let's quickly summarize what we've done so far. So basically, the whole P to C dot product with C to P is us creating the equivalent of local trust, like just what would have been the local trust input in eigentrust, right? So it's like we haven't changed eigentrust at all. We just have this extra added transpose step. So you still have the pre-trust, you still have a local trust. We're just creating that local trust in a different way.
Right.
And then reiterating, just reiterating that both the peers and the C, I forgot exactly what C stands for, but the tokens, they both still exist in this local trust. So there's technically two types of entities here. But again, the eigentrust formula itself is still the same.
Yeah. Yeah. Thanks, Andrew. Still using eigentrust as the building block, and eigentrust needs local trust, pre-trust, or seed trust, and alpha value. So we need all three parameters. Up until this point, we created the local trust from the peer to collection matrix. And then now we are moving on to creating or loading and pre-processing the seed trust or the pre-trust. And that's what I'm doing here. There are all these different variants of seed trust. We're trying to like load them from the CSV file that I locally downloaded. And then here each of these CSV files or each of these variants of seed trust may include peers that are actually not in the local trust. And those actually do not matter for the purpose of recommending anything. So we are just keeping those entries of seed peers that actually do appear in the local trust graph. And that's what's happening in this, because we have this peer map and we just need to find whether this like a given I in that ID or seed trust table. Actually, let me show you what that table looks like. Let's Zora and minters, for example. So here we see a bunch of addresses. This minters is a variant of seed trust where we put seed trust into first minters of any collection, and then that way we basically put more emphasis on those opinions who have at least minted at least one minted as the first minters or one of the first minters from any of the collections on Zora. So that's and this is basically the value or like how much they have minted once again. And this is actually a pretty long file. We have like roughly 70K and like first minters, but earlier we saw that we have only like 23K or 22K peers. So we're filtering out many of these guys who actually do not appear in the local and just keep those who actually do appear as like real seed trust. So that's what's happening in this code. Okay, so we do this. Yeah, it should take. So like out of these many entries, we only kept this many. This is so that you just see how effective. And then finally, we do this like eigentrust. This one actually does not use SDK, but what's called GoEigentrust, which SDK uses under the hood. This is basically a Golang based library / command line interface that you can also use locally. If you install this on your local laptop, like for example MacBook or like on like Linux on like Windows subsystem for Linux WSL, then you should be able to do this like same thing, on your laptop. I'm not gonna run this here because it takes a long time. But here, what we're seeing is like for each of these different seed trust, type ERC 721 count value, and also different alpha values, 0 to 1.2 or 0.1. We're doing this, and then we're saving that into global trust file here. So let me show you that global trust file looks like. All right, so this is basically that file. The I value are all integers, and these are basically the row indexes of the peers file, which we should have here. Zora means peers.csv, which was created earlier as we were local trust. So you see this index back to the name mapping. So you can do some sort of join. You can use some Python code to do that, to convert that global trust file back into the actual peer based ID, which is actually done. Dora mints GT. I think I did that. Yeah. So there's this raw version, which is the raw result that we get from GoEigentrust, the under the hood component. And then we map those results back into addresses. So GT up, no, minter 0.5 CSV. Yes. Oh, sorry, wrong minters. So you see that this one is now like referring to the actual peer ID as we got from the peers of CSV. And then for clarity, we also get what variant it was, what alpha value it was. We actually have this because we internally this to our Dune table for the dashboard. So let's recap what has happened so far. We created, or we got that peer-to collections data from Dune. We created peer-to-peer metrics using that, and then we ran eigentrust, and as a result, we got for each peer, for each person, we got eigentrust score. These scores indicate how strong their like relevance is under the given pretense, which is what seed trust we use. Like it will be used Minter's seed trust here with this alpha value 0.5, which is like a pretty strong alpha value. And then we have uploaded this table back onto Dune. And now let's jump to how this can actually be used. So let me go to the Dune. Change window. Let's go. All right, so we're gonna show you how we actually use this peer-to-peer based peer score, people score, and how we used to recommend mints. So let's first go to the data set that we uploaded, Minter's course. There is a public table called Zora mints GT. You see these four fields that we just saw. We merged them into all the we merged all the variants into this select distinct variant alpha. Yeah, so you see all these different. So we're gonna use this in theory. By the way, just to show you, looks like yeah, the same format that we saw. So let's go to the dashboard. Okay, so this is a pretty complex query, but let me just focus on what matters. We choose all the global trust, those V fields for each I. Basically, I is that like TX from minted. So why that's why we use name, and TX from score is basically that eigentrust score assigned to each of those peers. And then we filter a specific variant and specific alpha, which is based here. Okay. And then we choose from Zora.mints table. This is basically the same table that we used to create that IJV value in the first place. The P2C value actually came from that using the last 7 days worth of transactions. Here, we filter like the last 24 hours or message hours. And then we join with global trust that we pulled from here, from the data set, so that we only focus on those transactions performed by people with non-zero score in that global data set, And then we basically group all those transactions by summing per collection, and then the actual value that's being summed should be somewhere. Find that. See this? Oh, here we go. So collections. So we saw here what we're doing is from mints table, which is basically this filtered table using the global trust. Then we do this TX from score sum. TX from score is defined as here. This guy. TX from and then TX from score is here. Basically that that each person eigentrust score, and this total price USD TX from score USD is weighted price USD. Here, you can either use this or this as here. If we do this TX from score, then for each collection, for every single mint done by a person, that collection score is incremented by that. So if my score is 0.01, and if I minted 5 times, then the from the same collection, then that's collection score will be increased by 0.05. If we do this, then it's not just the number of times that I minted, but the actual dollar amount spent on that collection is also taken into account. So if I spent the actual dollar value, then it'll be used as a factor. For example, if my score is 0.01 and I minted from a collection and spent like $10 on it, then I'm basically adding which is 0.01, my score, multiplied by that USD dollar as the contribution for the collection. And then finally, we do the actual like ranking based upon those aggregated score. Like my contribution, Andrew's contribution, Dharma's contribution, everyone's contribution gets summed up for the same collection if we all minted from the same collection. And that's the sort key that we use to in order to recommend results. So let's actually do that and see what it looks like. There you go.
Yep, I could follow through.
There you go. Here we see, yeah, these. Now we see like this score that I explained, and then the contract address is basically which collection it is. I still need to hydrate this table by displaying the actual collection name, which is doable. I just found out how to do that yesterday, so I'm gonna make the change in afternoon. So yeah, that's what we did for this Zora NFT minting data set, and basically convert who has minted what data into eigentrust compatible local trust, did Hobson Authority's algorithm use trust, and converted that Hobson Authority's raw result back into usable recommendation, as you see here. I'll pause it here. Any questions, comments, or maybe any like notes? Andrew, Dharmi, do you guys want to add anything?
No, I feel like this was really good. I feel like you've nailed the examples and notes here. I'm excited to edit this video. I'll put together an article as well once we have the notebook public. I guess it'd be. I wonder if like I'm sure you're working on this already. It's like we can probably pass like maybe chunks of it through. Can I? Well, eigentrust can't be trained in chunks. Never mind. I don't know how we deal with the long compute issues on some of these. Because how big was this data set again in terms of the peers and collections?
So like raw peers to collection data is roughly 110K row, 117K to be exact. And if we create when we create peer-to-peer matrix for that, then the resulting peer-to-peer matrix has roughly 30 million non-zero entries. It's pretty big.
Right.
And this is from like last 7 days worth of minting history.
Right. I think we talked about this before in terms of like the more connected the data set is, then the larger the H&A matrix gets. So it's actually sometimes better to maybe have a more sparse matrix of the peer to collections. So it's an extra consideration here.
Right, but like that, this P2P matrix being big is basically a bullet that we need to bite, because if the data is like too sparse, then basically we end up getting a fragmented local trust, and a fragmented local trust is actually pretty bad, like recommendation quality. So yeah, there's that.
Right. And do we decide if we're giving this I don't know, we're calling this H&A, this is different from the credits, the interest in credits, right? Interest in credits.
Right. Yeah. This is Hobson Authority. It's not interest in credit. Interest in credit, the example is something different, and maybe we can do that in another office hour. We have another example that uses GitHub data. Yeah, for interest in credit.
Right. Yeah, because I think I may have shared some resources before with the open source observer model and then called it H&A. So just we should clarify that we'll be calling them different models.
Right. Open source observer is the first example that work done, and we are also working on some other data set